All right, welcome to part one of the lesson. So we're going to be reviewing a little bit of trees to start with. And there are two main ideas that we're going to be looking at. First is the tree diagram, and second of all is this whole idea of independence. And we're going to finish up with one last concept next lesson, and then we'll be completely done with this chapter. So let's start with a familiar example. So here we have flip a coin twice. What's the probability you get two heads? So I can represent this in the form of a tree diagram. So I can start with a coin, and there's two possible outcomes for the first flip. So it could either be heads or it could be tails. Similarly, on the second flip, there's two possible outcomes. It could be heads or tails. It could be heads or tails. So again, the first branching over here represents the first flip, and the second branching represents the second flip. Now, we're assuming that this is a fair coin, so we're going to assume that the probability of getting a heads or a tails is equally likely. So we're going to have probabilities of 1/2 for each of these branches here. Now, the question that was asked was, what's the probability that you get two heads? So the probability of getting two heads, getting two heads is represented by this top branch here. So it's going to be getting a heads on the first flip and then getting another heads on the second flip. Notice that it doesn't actually matter whether you got a heads or tails on the first flip. The probabilities for heads and tails don't change. And that actually is the beginning of the idea of independence. That's something that we've used before in this course, the idea of if you know something about an event, it doesn't change the probabilities of other outcomes. So the probability of getting heads and heads, you're probably familiar with the idea. We're going to multiply these two numbers together. So the probability of getting two heads is going to be 1/2 times 1/2, which is going to be 1/4. So this is a very simple example that I've used to kind of review a little bit about what you already know about tree diagrams. I imagine that this is pretty much review for most of you guys. So when is it better to use a tree diagram than a two-way table? Often it's best to use these when there's a sequence of events going on, like you flip a coin and then you flip another coin, or when there's a combination of more than two events. Then it's a little bit harder to see on a two-way table or in a Venn diagram. So if there's a sequence of more than two events, then a lot of times the tree is going to be your best bet. To find the probability of one particular branch, you're going to do just like we just did, and you're going to multiply along the branch. So the probability of getting a heads and then a tails would be 1/2 times 1/2. The probability of getting tails and then heads would be 1/2 times 1/2. So in order to find the total probability of more than one branch, so like we did, what we're going to do is we're going to find the probabilities of each of the branches separately. So for instance, in this case, each of these branches is going to give me a probability of 1/4. And then we're going to add together the probability of the branches that we actually care about. So if I asked a slightly different question, for instance, if I wanted to know what is the probability of getting more than one head, or of getting at least one head is probably a better one to use. If I say, what is the probability of getting at least one head, if I can get this thing to show up, there we go, then that's going to be the probability of those top three branches, the probability of getting heads and heads, the probability of getting heads and tails, the probability of getting tails and heads, and I would add together those three branches. Of course, for this particular example, to answer the question of what's the probability of getting at least one head, you could have used the complement rule. That is, you could have said, well, that would be all the possible outcomes except for this bottom branch here, the tails and then tails again. So that would be using the complement rule. The other way to get this is be 1 minus the probability of no heads. Either way should get you the same answer of 3/4. Okay, we're going to move to a slightly less trivial example. The Pew Internet and American Life Project finds that 93% of teenagers use the internet and that 55% of online teens have posted a profile on a social networking site. What percent of teens are online and have posted a profile? So I'm going to start by representing this with a tree diagram. So if I have a teen, there's two possible outcomes. Either they're online or they are not online. And I actually have some numbers here. So it says that 93% are online, which means that 7% are not. Now, then there's another thing, that they have posted a profile. So if they've posted, they could have posted a profile or not posted a profile. It says 55% of the online teens have posted a profile, so that's going to be 55%, which means 45% have not. This is a trivial example still, because if you're not online, then the probability that you have posted a profile is 0. The probability of not posted a profile is 1. So that's pretty simple. Remember, to find the probability of any one of these branches, you're going to multiply along the branch. So to answer the top question, what percent of teens are online and have posted a profile, you're going to do the top branch here, so it's 0.93 times 0.55, and you should get a total of 0.5115. Go ahead and take a moment, pause the video, and calculate the probabilities of the other branches. You should have gotten these numbers. Hopefully you did. If I didn't do my math incorrectly. So again, to answer the question, what percent of teens are online and have posted a profile, that's going to be this number here. So we're going to say about 51% of teens. But if I asked a slightly different question, what percent of teens have not posted a profile? Well, there's two possible ways that could happen. They could be online and not posted a profile, or they could not be online and not posted a profile. So one way to answer that question would be to get those two branches and add together those two numbers. So 0.4185 plus 0.07, I get a total of 0.4885. The other way to do it is to realize that, well, this branch doesn't really count because it's just 0. So you could have said, all right, well, it's going to be everybody except these 51% that are online and have posted a profile. So again, you could have got this one using the complement rule as well. All right, let's move on to one that's a little bit more complicated. So in January 2010, the Kaiser Family Foundation released a study about the influence of media in the lives of young people. In the study, 17% of the youth were classified as light media users, 62% were classified as moderate media users, and 21% were classified as heavy media users. Of the light users who responded, 74% described their grades as good, while only 68% of the moderate users and 52% of the heavy users described their grades as good. According to this study, what percent of young people describe their grades as good? I'll get you started on this one. So we're going to start with a random young person, and we're going to classify them by media usage. So there's 3 different possibilities here: light media, moderate media, and heavy media. Then comes the grades. So either their grades were good or we're going to say not good. So this is what the tree should look like. Go ahead and pause the video here, take a moment, and fill in the numbers where they should go. Hopefully these are the numbers that you got. Now, in order to answer this question, what percent of young people describe their grades as good, there are 3 different branches that I'm going to care about then, because they could have had light media usage and had good grades, moderate media, or heavy media. So go ahead and calculate the total probability, what percent of young people describe their grades as good. Hopefully you got the same answers that I did. So these are the numbers for those branches. So my total probability is going to be, this number right here, about 66%. All right. For trees, my best advice to you is to practice with these. The more practice you get, if you do all the homework problems, that should be a good start for getting you ready for this. The other big concept is, how can you tell if 2 events are independent? This is in the guided reading notes, and you probably saw something like that. The idea of independence is the idea of whether knowledge of one thing gives you any knowledge about another thing. So for instance, if I asked you, what is the probability that I pick a random student at Westfield High School and their SAT score was 2300 or better, you probably can come up with some number. Now if I say, all right, given that I pick a female student, what's the probability that their SAT score is 2300 or higher? So the first one was, if I just pick a random student, what's the probability of a high SAT score? And the second one was, suppose I pick a female student, among only the female students, what's the probability? And if your answer in your head did not change, then you believe that those two things are independent. You believe that gender and whether or not you get a high SAT score are independent of each other. So the way this works is two events are independent if the probability of one event, given that you know another one is true, is still just the same as the probability of that event. So written in symbols, it looks like this. Two things are independent if and only if the probability of A, given that B is true, is the same as the probability of A. So the if and only if means this goes both ways. If you know two events are independent, that means the probability of A given B is exactly the same as the probability of A. And if you know that the probability of A given B is the same as the probability of A, that is how you can prove that two things are independent. Now, a consequence of this, not the definition of this, if you look on your formula sheet, and if you haven't already, pause the video and get it out, like for real, because you need to know this. On the formula sheet, if you look on the second page under the second Roman numeral and the second formula down, it says the probability of A given B is equal to the probability of A and B divided by the probability of B. Do you see it? So a consequence is that if two events are independent, the probability of A given B is exactly the same as the probability of A. So that means instead of where it says A given B, we can put in the probability of A instead. So the probability of A is equal to the probability of A and B over the probability of B. If you do a little bit of multiplying here, that means the probability of A and B is equal to the probability of A times the probability of B. We're going to do more with this next class because that's really the only one concept that I want to have a little bit more time to go over with you guys. So let's do a quick example. Here is the example that we used last time. So here's gender versus whether or not a person has their ears pierced. And we're going to go ahead and put in some totals so it's a little bit easier to find probabilities. The first question is, what is the probability of a male having pierced ears? So this is not just the probability of a random person having pierced ears. In fact, maybe we should do that first. So what is the probability of just anybody having pierced ears? The probability of just a person having pierced ears is going to be 103 out of 178. These are different questions. What's the probability of a male having pierced ears? So it's not out of everybody, it's only out of the males. So what's changing is going to be my denominator. So what's the probability of a male having pierced ears? It's going to be 19 out of 90 because I'm doing it only out of the males. So that's going to be the probability that someone has pierced ears given that you know that they are male. It's going to be 19 out of 90. The probability of a female having pierced ears. So here are people that have their ears pierced and are female, and it's going to be only out of the females. So my denominator is going to be 88. So the probability of having pierced ears given that someone is female is going to be 84 out of 88. So now here is a very common question. So a lot of times they will ask you something like, part A, what's the probability someone has pierced ears? Part B, what is the probability of a male having pierced ears? So what's the probability of having pierced ears given that someone is male? And then part C might be, are these two things independent? And all you really have to do is, because remember the definition of independence, all you have to do is see if the probability of A is the same as the probability of A given B. So here we have the probability of having pierced ears versus the probability of having pierced ears given that you are male. You probably don't even have to put these numbers into a calculator to determine that these numbers in fact are not the same. Doesn't reduce to anything that's the same. So the answer is no, they are not independent. You could have done it the other way too. You could have said, all right, well, what is the probability of being male versus the probability of being male, of having pierced ears given that someone is male? And if you chose to do it that way, it's just another way to do it. Last thing before well, there's a couple more examples. But what's the difference between mutually exclusive and independent? So mutually exclusive I talked a little bit about last time. Here is a quick and dirty Venn diagram of freshmen and people who are taking AP Stat, and they are mutually exclusive. So we said, all right, the probability that someone is a freshman and taking AP Stat is 0. So that intersection, the probability that they are a freshman and they are taking AP Stat is equal to 0. Now, that's what mutually exclusive means. Independent, and for some reason people get these confused all the time. Independent means what we said earlier. The probability of A given B is equal to the probability of A. It does not matter whether you know B has occurred or not. So if you think about this, the probability of being a freshman and taking AP Stat is 0. So if I know someone is a freshman, the probability that they are taking Stat is 0. So these events are actually not independent, because if I say, well, what's the probability a random person is taking Stat? And you have some number in your mind, maybe 5% or something. A random student at Westfield is taking AP Stat. Well, then I say, all right, well, what's the probability they're taking AP Stat given that they are a freshman? That number is now 0. So these are two different ideas. One is the idea of they are disjoint, they cannot be in both groups at the same time, their intersection is 0. And the idea of the probability of A given B is exactly the same as the probability of A. So these are two different ideas, but the idea is they can't be both at the same time, because if they are mutually exclusive, and you tell me someone's a freshman, I already know something about the probability of whether or not they're taking Stat. So two things cannot be mutually exclusive and independent at the same time. Okay, that's good for part A, or part 1. Go ahead and, this video is coming to an end, so I'll see you guys on the other side.